Today I want to talk to you about a polynomial regression. So we're going to explore the data set visually, we're going to implement and discuss what is polynomial regression, discuss the assumptions of regression, and then go over evaluation metrics for model comparison. So in this data set, we want to predict the miles per gallon of the car based on its weight. So to start this investigation, we are going to visualize that, the scatter plot of these two variables. Okay. We see that there's 6 missing observations in horsepower, so we simply remove those the missing observations. Okay. So one question we're implicitly asking is, does weight affect miles per gallon? So let's make the graph of this. So this is the graph of it. It appears that weight does affect it. One question is, would it affect it linearly or would it affect it quadratically? Okay. So in this instance, for a quadratic regression model, it will simply be beta 0 plus beta 1x plus beta 2x squared. So x here is weight. Okay. Now there's no reason to stop at a squared term. We could go up to any degree p polynomial. So most common are second or third degree polynomials. It's not typical to go too far beyond that. Now we're going to compare this quadratic model with just a model in which b2 is 0. We just have b0 plus b1x. That is a linear model. Okay, so here I fit a linear model and I fit a quadratic model. We see here that there's this green point, this green line, that's the quadratic one, and then there's this red line here. The question is, do you believe that the curvature of this data more resembles a quadratic equation or a linear equation? I think visually there's an argument for both, although it appears slightly, and not obviously, that the quadratic could be a slightly better fit because it better fits the points right here. Okay. Now, to help us evaluate this, we can use the r squared and the RMSE value. We could also use p-values. That would be the most useful metric. However, the library sklearn does not have p-values as easily built in as the stats model implementation. Okay, so we'll make our decision based off of RMSE and r squared. Okay. Now, we calculate it for each, and for the linear regression model, we'll get an RMSE, root mean square error, of 4.32 versus 4.16 for the quadratic. Now the quadratic, it comes at an extra expense. So the extra expense is that we have to estimate 3 parameters, beta 0, beta 1, and beta 2, whereas the linear regression line, you just have to estimate 2 parameters. The problem with estimating more parameters is a statistical one. The more things you have to estimate, the more likely you're to get one of the estimates wrong. So the fewer terms you can estimate, generally the better, but you have to weight that against the improvement in the model performance. So while 4.32 is higher, it's not that much higher than 4.16. So you have to ask yourself, is that small reduction in RMSE worth it? Okay, to estimate an extra parameter. Okay, the r squared here is 69%, 69.2, and we do not adjust for linear regression, but we do adjust when there are more than 2 variables, or 2 or more variables in our model. So in this case, our variables are x and x squared. Okay, so when we have more than 2 parameters to estimate, in other words. Okay, so in general, we adjust when we have more than 2 variables or when we have a quadratic or higher model. Okay, so when we adjust, we get 71.29, and this is a more conservative estimate for the r squared, and we compare that to 69. So this does improve the r squared. The question is just, is it worth it? So there is evidence for yes. There is also an argument for no. So it's not a shut and closed case. It is up to the modeler. But if you were to see a big jump in r squared, or adjusted r squared, and generally a big jump is like 5% or more. I've seen anywhere from 5% to 50%. That would be an indicator that you want to include that variable. Certainly a jump of like more than 10% is a really good indicator. In this case, it's a moderate increase. It's at your discretion if you view that it's worth it. I think some people would say it depends on your purpose. If your purpose is to better model the data, the quadratic may be a better fit. If you simply want statistical inference, the linear regression would be the better model. Okay, so this is one of an instance where it's not so cut and dry. Now we can use the MPG of the car to make predictions. Okay, so based on a 2,000-pound car and a 2,500-pound car, we can see that using linear regression for 2,000 pounds, our estimated MPG is about 31 versus 2,500 is 27. Okay, for a quadratic, it's 32 for the 2,000 versus 26.6. So a little bit of a different estimate, but both within reason. Okay. Now, a third way to make decisions based off of which model to use would be which one meets the assumptions of regression. The assumptions of regression are normality in the error terms, constant variance, and independence. We should note we have independence because it's not like, because one car's MPG does not affect another car's MPG. So they're independent. Okay. For the normality, we'll use histogram of the residuals and QQ plot of the residuals. One of them is sufficient, but I just thought you should know that you could use both. Okay. So let's go through this. The assumption of the residuals for the quadratic model looks like this, and it looks relatively normal. You know, certainly not everything meets exactly the theoretical values, but the overall shape seems reasonable. Okay. Now here's the QQ plot. There's some departures from normality here. This is concerning. Okay. So based on two different graphs, you can draw somewhat similar and somewhat different conclusions. So this is concerning right here, but you could also say this is concerning right here, that the apex is both higher and a little bit askew from the normal distribution. So there's a little bit of evidence in each graph. So my overall assessment of normality is that normality is not completely met, but is reasonably approximated. Okay. Now, for constant variance, if we look at this plot of the residuals, we see that the variation is relatively small for when the predicted miles per gallon is small, meaning you get more accurate predictions. But when the predicted MPG is high, there's more variability in the error. So it looks like there's slightly non-constant variance in this data. So I would say a small violation to the assumption of constant variance. Okay. So again, we're just looking at the same graphs. It repeated itself twice. So overall, those are things that you should pay attention to and think about when you're implementing polynomial regression. Thank you very much.